These three properties are the pillar of distributed system, but here is the catch. You can only fully achieve two of the three at a given time. So consistency basically ensures that every read receives the most recent write or an error. This means that all working nodes in a distributed system will return the same data at any given time. To illustrate this, think of about Google Docs. So if you lose your internet connection while editing a document, you can still make changes locally. So what it essentially shows? So it shows a network partition. With this choice, your system will keep data consistent even during network failures. However, it might become unavailable in those moments to maintain data integrity. Hey there, welcome to Prep Train, your go-to channel for mastering concepts, building skills, and advancing in your career. I am Sahib Kumar and I'm super excited to have you here today. At Prep Train, we are all about simplifying complex topics, providing actionable insights, and helping you grow, whether it's for your next job, project, or just to expand your knowledge. Now, let me ask you something. Have you ever wondered how apps like Instagram, Twitter, or even your favorite banking app stay up and keep running no matter what? Or why some app basically prioritize real-time data accuracy while others focus on staying accessible 24/7? Well, today we are diving into a fascinating world of CAP theorem, a fundamental concept in distributed system that basically explains the trade-offs every system designer basically face. So trust me, understanding this will completely change the way you think about system design and backend engineering. But before we jump in, take a second to hit that subscribe button and turn on notification. That way you won't miss out on any upcoming videos packed with insights and tips to level up your backend engineering skills. And if you do find this video helpful, a quick like would mean the world to us. All right. Also, don't forget to join our Prep Telegram community on Telegram. It's a great place to stay updated on latest job and internship opportunities, as well as connect with other fellow programmers who are passionate about learning and growing in the tech field. So let me just fetch my deck and then we will dive deeper into the topic of CAP theorem. Stay tuned. The CAP theorem, which stands for consistency, availability, and partition tolerance, encapsulates this challenge. These three properties are the pillar of distributed system, but here is the catch. You can only fully achieve two of the three at a given time. This means that as architect of a distributed system, we need to make tough decisions about what to prioritize based on the application requirements. Let's unpack these terms briefly. So basically consistency ensures that every read operation receives the most recent write, which is essential for real-time accuracy. Availability basically guarantees that every request receives a response even if it's not most up-to-date one. Partition tolerance ensures that the system continues to function despite communication breakdown between different parts of the system. Now look at the Venn diagram on the slide. So this figure helps illustrate the trade-offs in action. So the overlapping areas like combinations like CA shows consistency plus availability, CP shows consistency plus partition tolerance, and AP shows availability plus partition tolerance. Notice, however, the center of Venn diagram, this area is basically where all the three properties meet is empty. That is because no system can achieve all three simultaneously. This is the fundamental limitation that CAP theorem highlights. Now that we have introduced the CAP theorem and its key concepts, let's dive deeper into each property starting with consistency. Now let's zoom in on the first property of CAP theorem, consistency. So consistency basically ensures that every read receives the most recent write or an error. This means that all working nodes in a distributed system will return the same data at any given time. To explain consistency, imagine that you are using an online banking app. So if you transfer money from one account to another, you expect basically the balance to update instantly. And anyone accessing your account from another device should see the same updated balance. And that is we mean by consistency. So every user interacting with the system sees the same data at any given time. But here is how it works in distributed system. When a change is made to data on one node of the system, that change is immediately propagated to all other nodes. So this ensures that all nodes are synchronized and provide the same information no matter where the request is made. So consistency is especially important for applications like financial system, inventory management, and collaborative tools. So for instance, take Google Docs. So when two users are editing the same document, consistency ensures that one user update are immediately visible to the other. Without this, the collaborative experience would fail apart. However, the consistency often comes with trade-offs. So achieving it may increase latency because system needs to ensure that all nodes are updated before confirming a request. So this can make consistency challenging in scenarios where real-time speed is a priority. Now that we have understood consistency and its significance, let's move on to another critical property of CAP theorem, availability, where the focus shifts to keeping the system responsive at all time. Let's now explore the second property of CAP theorem, availability. So availability basically guarantees that every request, read or write, receives a response without ensuring that it contains the most recent write. This means that the system remains operational and responsive even if the response is from some of the nodes that don't reflect most up-to-date data. To understand availability, imagine shopping on Amazon during a major sale, like say Black Friday. So even with a million of users accessing the platform simultaneously, the website rarely crashes. How does Amazon achieve this? By prioritizing availability. It ensures that requests are handled promptly even if some part of their infrastructure are down. That's how availability works in distributed system. When a user makes a request, the system basically guarantees a response even if it is not most up-to-date data. This is critical for applications that handle high traffic like e-commerce platform, streaming services, and social media apps. However, there is a trade-off here as well. To ensure high availability, the system might occasionally sacrifice consistency. For example, in an online shopping app, the inventory count might momentarily show outdated information if the system prioritizes basically responding to requests over updating data in real time. Now that we have seen how availability keeps system responsive, let's move on to the third and final property of CAP theorem, partition tolerance, which basically focuses on resilience in the face of network failures. Finally, let's discuss the third property of CAP theorem, partition tolerance. So partition tolerance means that the system continues to function despite network partitions where nodes cannot communicate with each other. To illustrate this, think of about Google Docs. So if you lose your internet connection while editing a document, you can still make changes locally. Once the connection is restored, those changes sync with the rest of the system. This resilience in the face of network disruptions is what we mean by partition tolerance. Partition tolerance is essential for distributed systems that operate across different regions or rely on multiple data centers. Network failures basically can happen for various reasons, including hardware issues, natural disaster, or even routing problems. So when these failures occur, partition tolerance ensures that the users can continue working with the system even with some limitation. However, prioritizing partition tolerance often comes at the expense of either consistency or availability. For example, during a network partition, some nodes might not have the latest data, which affects consistency. Alternatively, the system might delay response to maintain consistency and it impacts availability. Take a look at the diagram on this slide. So what it essentially shows? So it shows a network partition. Basically, a break in the connection between servers. So despite the break, users on the other side of the partition can still interact with the system. This ensures that system remains operational until the network issue is resolved. Now that we have covered all three properties, consistency, availability, and partition tolerance, let's discuss the real challenges, how to make trade-offs and decide which two properties to prioritize on the basis of your system needs. Okay, now that we have reached the heart of CAP theorem, the trade-offs. So basically the slide here shows the critical decision every distributed system designer must take. So you can only choose two of the three. So consistency, availability, or partition tolerance. Let's dive into what these choices mean and why they matter. First, let's talk about consistency and availability. So CA. So basically, your system will ensure accurate data and quick response. However, it won't tolerate to network partition. So this setup works well for system in controlled environments where network issues are rare. For instance, like say traditional database like MySQL often prioritize CA, so ensuring data accuracy while being highly responsive. Next, we have consistency and partition tolerance or CP. So basically, with this choice, your system will keep data consistent even during network failures. However, it might become unavailable in those moments to maintain data integrity. This trade-off is ideal for system where data accuracy is paramount, such as financial application. So imagine that a banking app users would rather wait a bit longer than the risk of basically inaccurate transaction. So system like HBase often prioritize CP for this reason. Finally, we have availability and partition tolerance AP. So this trade-off basically ensures that your system remains operational even during network issues, but it may serve a slightly outdated data. So this approach is perfect for high traffic platforms where uptime is crucial, such as Cassandra. So it powers basically social media apps. So for instance, if Instagram is slightly delayed in updating your feed but it remains accessible, users typically find this acceptable. So the diagram on this slide basically represents this concept with a triangle. So each side of the triangle basically represents one trade-off combination. So these sides, and you can't have all three at once. So system architects must carefully evaluate their priorities based on the application requirement. With these trade-offs in mind, let's look at some real-world systems that have implemented these strategies effectively. All right, so let's talk about some real world example of systems and how basically they align with different trade-offs that we just discussed. Let's start with CA. So systems like MySQL, these systems prioritize consistency and availability, making them ideal for real-time applications that need fast and accurate responses. Think about traditional enterprise application where network partitions are rare and data accuracy is critical. So MySQL ensures that every query gets an accurate response quickly, but it might not be the best choice for highly distributed system where partitions are more likely distributed. So then we have CP systems such as HBase, which are widely used in financial services. This system prioritizes data consistency even during network failures. So imagine that you are transferring money between accounts. So the system must ensure that the transaction is recorded accurately even if part of network is temporarily offline. By sacrificing availability during network failure, this system basically guarantees that no inconsistency occur, which is essentially for building trust in financial transaction. Lastly, let's look at AP system like Cassandra, commonly used by social media platforms. So these systems prioritize availability, ensuring that they are always responsive even during network partition. For example, Instagram prioritizes keeping the app up and running at all time, even if the data shown is slightly out of date while syncing. So users prefer this approach because they value accessibility over perfect accuracy in real time. Now that we have seen how these trade-offs are applied in practice, let's explore some well-known companies and the CAP priorities they use to design their system. Now let's take a closer look at how well-known companies apply the CAP theorem in their system design. This will help us connect the theoretical trade-offs to real-world example that you are familiar with. First, let's take a look at Instagram. As a social media platform, Instagram prioritizes availability and partition tolerance, which is AP. So the goal is to ensure that users can always scroll, like, and post without interruption. Even if some part of network fail, for instance, when you upload a photo, the system prioritizes making it immediately available to other users. However, some data like an updated like count might be, like lagging behind when the system syncs. So this trade-off makes sense for a platform where responsiveness and uptime are crucial. Now think about banking apps. So these systems basically prioritizes consistency and partition tolerance, which is CP. So accuracy is basically absolutely essential when handling sensitive transaction like deposit or fund transfer. So imagine that basically you are transferring money from one account to another, and if the system displayed inconsistent balances, it would be breaking the user trust. So to ensure that data accuracy, banking apps may sacrifice availability during network issues. You might experience temporary shutdown, but when the app is back online, you can be confident that your financial data is correct. Lastly, let's consider a streaming platform like Netflix. So like Instagram, these systems basically prioritize availability and partition tolerance, and Netflix primary goal is to keep video streaming without interruption. And even if part of its network goes down, for example, if a server in one region becomes inaccessible, Netflix reroutes traffic to ensure that the video keeps playing. You might not immediately see an updated watch history, but the streaming experience remains seamless. Now that we have seen the CAP theorem in action, let's summarize the key points that we discovered so far and tie everything just back together. Alright, So we have covered a lot today. So let's take a moment to summarize the key takeaways from our discussion of CAP theorem. First, in distributed system, you can only choose 2 out of 3 properties: consistency, availability, or partition tolerance. This is the core trade-off that defines how these systems are designed. If you prioritize consistency and availability, your system will deliver accurate and fast responses but won't tolerate network partition. This is best suited for environments where partitions are rare, like traditional enterprise application. For example, MySQL is a good choice when CA is the priority. But if you prioritize consistency and partition tolerance, your system ensures data accuracy even during network failures, but might become temporarily unavailable. This is the right choice for applications where data integrity is critical, such as financial systems like HBase. Finally, if you prioritize availability and partition tolerance, which is AP, so your system will always be responsive even during network issues, but some users might see slightly outdated data. This trade-off is ideal for high traffic applications like social media and streaming platforms where uptime is crucial. So systems like Cassandra are built with AP in mind. And that wraps our deep dive into CAP theorem. I hope that you now have a solid understanding of consistency, availability, and partition tolerance, and how these trade-offs influence the system that we rely on every day. If you found this video helpful, do give me a quick favor, give it a thumbs up, and it really helps the channel grow and let us know that we are on the right track. And also, don't forget to hit the subscribe button and turn on notifications so that you are always the first to know whenever our next video drops. Also, I did love for you to join the Prep Train community on Telegram. It is a fantastic place to stay updated with latest job and internship opportunities, as well as connect with like-minded learners and professionals. You will find the link in the bio of this channel. And at Prep Train, basically, we are committed to bringing you more engaging content, especially around backend engineering and system design. So stay tuned because there is much more things coming your way. Thanks again for watching. This is Sahib Kumar signing off for now. Keep learning, keep growing, and I will see you in some other video.